Welcome to the next class on Advanced Functional Analysis. We are continuing our section Fredholm Theory of Compact Operators. Today we will discuss two examples. The first one is integral operator in the form Fredholm's operator. So, suppose t of xt is equal to integral a to b k of t tau x of tau d tau, where this x may be in CAB or in L2 of AB. Then we will consider the operator defined by t lambda of x of t is equal to y of t. We are considering this operator t lambda of x of t is equal to y of t. So what is meant by t lambda of x of t? It is t of x of t minus lambda times x of t, means integral a to b k of t tau x of tau d tau minus lambda times x of t. We will call this by y of t, and here I am taking lambda not equal to 0. Then we may rewrite this as, now what we have is y of t is equal to minus lambda times x of t plus integral a to b k of t tau x of tau d tau. Divide throughout by minus lambda. So we will get x of t plus minus of 1 by lambda times integral a to b k of t tau x of tau d tau is equal to minus 1 by lambda y of t. Now we will write 1 by lambda as mu, so this equation will become x of t minus mu times integral a to b k of t tau x of tau d tau is equal to minus mu times y of t. Suppose this lambda is an eigenvalue, or if y is equal to 0. Suppose here in equation 1, in this equation, if y is equal to 0, then the equation will be t lambda of x of t is equal to 0. Suppose, or t of x of t minus lambda times x of t is equal to 0. Suppose this equation has a non-zero solution x of t. There is some x not equal to 0 such that this t of x of t is equal to lambda times x of t. That means this lambda is an eigenvalue of the integral operator t. Okay, so let y equal to 0 in 1 so that we will get this equation. If this equation has a non-zero solution x of t, then lambda is an eigenvalue of the integral operator. So if x of t is the solution, is a solution of this equation, then we can say that if we divide this throughout by minus lambda, we will get x of t minus mu times integral a to b k of t tau x of tau d tau is equal to 0. And this means mu is a characteristic number of the integral operator. This is a Fredholm operator. If it is in this form, the constant appears here is known as characteristic number of the integral equation. So whenever lambda is an eigenvalue of the integral operator t, 1 by lambda, that means mu, which is equal to 1 by lambda, is a characteristic number of the integral equation, and vice versa. So we can say that mu is a characteristic number of the integral operator if and only if lambda, which is equal to 1 by mu, is an eigenvalue of it. And we know that then if lambda I converges to 0, as mu converges to infinity. Whenever lambda I converges to 0, corresponding this lambda I means different values of the lambda i's are eigenvalues. Eigenvalues of t if lambda i's are the eigenvalues of t, lambda I converges to 0 as mu converges to infinity. In this case, we have considered a Fredholm operator. Now we will take one Volta operator. So here I am taking x as c01 and k of t to be a continuous function. The operator t from x to x, which is denoted by t of x of t, is equal to integral 0 to t k of t to d to k of t to x of to d to is known as a Volta operator. We know that if both the limits of integration are constants, we will call it a Fredholm operator, and if one of the limit is varying, then we will call it Volta operator. So here we are taking a Volta operator. So t of x of t is equal to integral 0 to t k of t to x of to d to. Here we are taking x from c01 and k of t to is a continuous function on 01 cross 01. Now we will consider the equation I minus t of x of t, which is equal to x of t minus tx of t, which is equal to x of t minus integral 0 to t k of t to x of to d to, and we will denote this operator by y of t. Now we will show that this equation has a solution for every y element of C01. For every y element of C01, we will prove that this equation has a solution. So currently the equation we have is minus of t lambda of x of t is equal to y of t. This is equation 1. We will prove that this equation has a solution for every y element of C01. For that, we know that k of t to is a continuous function on 01 cross 01. So this is a continuous function on a closed bounded interval, hence it is bounded. Similarly, y element of C01. So y is a continuous operator on the closed bounded interval 01. Then y is also bounded. So we will take c and c1 as positive real numbers such that absolute value of k of t2 less than or equal to c for every ordered pair t2 element of 01 cross 01, and c1 is chosen such that absolute value of y of t less than or equal to c1 for all t element of closed interval 01. So we can write equation 1. Equation 1 is x of t minus t of x of t is equal to y of t. So we can write this as x of t is equal to y of t plus t x of t. So x of t is equal to y of t plus t x of t is integral 0 to t k of t to x of to d to. Now I am taking x naught of t as the constant function 0. X naught of t is taken as constant function 0. So on the entire interval closed interval 01, x naught of t assumes the value 0. And xn of t is defined as y of t plus integral 0 to t k of t to xn minus 1 of to d to for all n element of natural numbers. Now absolute value of x1 of t minus x naught of t will be same as this will be absolute value of x1 of t can be written as y of t minus plus integral 0 to t k of t to x naught of to means 0 d to minus x naught of t 0. So this term will be 0. This is also 0. So what remains is y of t. So absolute value of y of t. And we know that absolute value of y of t is less than or equal to c1. I can write the c1 as c1 times c of t to the power 0 divided by 0 factorial. That means 1 minus 1 factorial. Now I will check what is absolute value of x2 of t minus x1 of t. That will be same as integral x2 of t can be written as y of t plus integral 0 to t k of t to then x1 of t is y of t minus x1 of t means y of t. So y of t and y of t will get cancelled. So what we will get is absolute value of integral 0 to t k of t to y of to d to, and this will be less than or equal to integral 0 to t absolute value of k of t to times absolute value of y of to d to, and this is less than or equal to c times c1 integral 0 to t d to, and integral 0 to t d to will be t. So we have c1 c t. I can write this as c1 times ct. This is c1 times ct to the power 1 or ct to the power 2 minus 1 divided by 1 factorial, which is 2 minus 1 factorial. Now I'm assuming that sorry, absolute value of xn minus 1 is less than or equal to c1 times ct to the power n minus 1 divided by n minus 1 factorial, and I will check it out what is an upper bound for absolute value of xn plus 1 minus xn. Absolute value of xn plus 1 minus xn can be written as absolute value of xn plus 1 is y of t plus integral 0 to t k of t to xn of to d to minus xn of t can be written as y of t plus integral 0 to t k of t to xn minus 1 of to d to, so that y of t will get cancelled. Both integrations have the same limit 0 to t, so we can combine them. Then what we have is integral 0 to t k of t to xn of to minus xn minus 1 of to d to. Okay, so this is less than or equal to, again this is less than or equal to this absolute value of k of t to is less than or equal to c. So we can say that this is less than or equal to c integral 0 to t absolute value of xn of to minus xn minus 1 of to d to, and by our assumption this xn of t minus xn minus 1 of t is less than or equal to c1 ct to the power n minus 1 divided by n minus 1 factorial. So here we can write this is less than or equal to c, then c1 c to the power n minus 1 divided by n minus 1 factorial integral 0 to t to the power n minus 1 d to. Since integration is with respect to to, we have to keep this to power n minus 1 as the integrand. So what we have is, so this is nothing but C1 C times C power n minus 1 is C power n. Then tau to the power n minus 1. Integral of tau to the power n minus 1 is tau power n divided by n between limit 0 to t, which is nothing but t power n by n. So we will get t power n divided by n minus 1 factorial times n is n factorial. So this is C1 Ct to the power n by n factorial. So whenever absolute value of xn minus 1 is less than or equal to C1 times Ct to the power n minus 1 divided by n minus 1 factorial, we have absolute value of xn plus 1 of t minus xn of t is less than or equal to C1 times Ct to the power n divided by n factorial. Means by mathematical induction we can say that absolute value of xn plus 1 minus xn is less than or equal to C1 Ct to the power n divided by n factorial for every n element of natural numbers. Here this t is in closed interval 0, 1. If t is less than 1, then we know that t power n converges to 0 as n tends to infinity. And suppose if t is equal to 1, so the numerator is independent of n, and 1 by n factorial converges to 0 as n goes to infinity. So in any case, as n becomes larger and larger, absolute value of xn of t minus xn plus 1 of t minus xn of t will converge to 0. Okay. So the right hand side converges to 0 as n tends to infinity. So LHS also converges to 0 as n goes to infinity for every t element of closed interval 0, 1. Thus, sequence xn is a convergent sequence in C0, 1. Also, but the series summation over n C1 Ct to the power n divided by n factorial is a convergent series, so that we can write and we can write xn is equal to summation I is equal to 1 to n xi minus 1. The series summation k equal to 1 to infinity xk minus 1 is a series which is dominated by this convergent series. Therefore, this series is convergent absolutely as well as uniformly. But summation k equal to 1 to infinity xk minus 1 is equal to limit n tends to infinity xn. So that means limit n tends to infinity xn converges uniformly. So if we call the limit of xn as x, so this is the uniform limit of a sequence of continuous functions. Therefore, x will be in C0, 1. So our equation 2 means xn of t is equal to y of t plus integral 0 to t k of t tau xn minus 1 of tau d tau. If in this equation, if we take limit as n goes to infinity, we will get x of t is equal to y of t plus integral 0 to t k of t tau x of tau d tau, or x of t minus integral 0 to t k of t tau x of tau d tau is equal to y of t. Means x of t is a solution of our equation I minus t of x of t is equal to y of t. So this equation has a solution x of t here. So what we get is x of t minus integral 0 to t k of t tau x of tau d tau is equal to y of t has a solution for every y element of C01. which means that the operator I minus t is an invertible operator. If I minus t is an invertible operator, t minus I is also an invertible operator, or we can say that 1 is not an eigenvalue of t. If 1 is not an eigenvalue of t, we can say that 1 is not in the point spectrum. So in a similar way, we can prove that whenever lambda not equal to 0, lambda is not in the point spectrum of t. Or we can say that the point spectrum minus singleton 0 is an empty set.